Hi guys, and by the end of this video you should have a thorough understanding of number bases and be able to convert between them.
That means binary, hex,
base 64, not just those, any number base. Most of you are probably here for binary or hex, and I can tell you how to do that in less than 5 minutes, but we're going to give you the lesson that our dad gave us when we were younger, so then you'll have a thorough understanding and you won't be restricted to just binary or hex. You can apply your knowledge to any number base. This is going to be really important if you're following along with our videos, and if you're hacking, cracking, coding, you're going to come up against binary and hex, so this is going to be a really useful thing to know.
By the end of this video, you will also be able to decode this secret message.
Before we get started, let's look at some examples of different number bases
in the wild.
Time for our first example of a number base in the wild. What you're looking at here is some hex, also known as hexadecimal or base 16, and next to it you can see it translated into some parts English. And this is actually the first ever Bitcoin block, also called the Genesis block. Bitcoin, as most of you will probably already know, is a form of cryptocurrency, and at the moment, one Bitcoin is equal to about $61,000. A different number base example here. I'm composing a new email with an attachment of a photo of my little sister. You can see here our email. I'll click this and then I'll download this email so that we can see the raw source of it, and I'm opening it up with VS Code. Now there are quite a few recognisable parts of this email, such as the subject, the file name, the message, and all this stuff here is a massive example of base 64. And you can see all sorts of symbols here, not just the usual numbers that we're used to.
In the video where we played and explained the RGB LED, we used the hex number to determine the colour of the RGB LED. You can see this colour represented here. 0x here just means it's a hex number. The first 2 digits is how much red the colour has, the second 2 digits is how much green, and the last 2 digits is how much blue the colour has. You can see that colour here.
I'll be doing binary.
I'll be doing decimal.
Binary is base 2. My job is easy. Binary or base 2 have only 2 digits, 0 and 1. I moved all digits up here for space. This comma's a bit confusing.
Decimal, also known as base 10, as we know, has 10 digits, 0 through to 9. These digits don't necessarily have to look like this. For example, 0 could be represented as a triangle, 1 could be represented as a swirl, and 2 could be represented as a tree. That is a very bad tree. When I was younger, my dad actually replaced all of these values with different symbols to prove to us that it doesn't really matter what the digits look like. But I've been through that, so to keep things simple, we'll just stick with the digits that we've come to love and know. In any number base, we have these grids. Usually in the centre we'll put a point. I'm going to put it here. At the moment we're not going to worry about the point or anything to the right hand side of it. We're only going to focus on everything to the left hand side of the point. This is representing any number base. In the first column we have b to the power of 0. If you don't understand this at the moment, don't worry because I'm going to be going through it. The next column we have b to the power of 1, and then we have b to the power of 2, b to the power of 3, as you can probably guess, b to the power of 4, b to the power of 5. I know there's those of you watching who know all about all of this stuff that I'm teaching in this video, and I don't want to seem patronising to you guys, so I'll just let you know that this video I'm going to be explaining to those of you who maybe have come to this video knowing absolutely nothing about bases, number systems, or even what indices are. And if you're one of those people, then kudos for sticking around.
My sister says this works for any number base, so I'll do exactly the same on my board.
If you're unfamiliar with what these little numbers are, these are indices, and my little sister has got a great video explaining in detail what indices are. So if you want to find out about them, then go check that video out now. If not, I'll just briefly explain to you what they are. Let's talk about these little numbers very briefly, indices or exponents. b to the power of 2 is just b multiplied by itself 2 times. What about b to the power of 4? Well, that's just b multiplied by itself 4 times. b multiplied by b multiplied by b multiplied by b. 1, 2, 3, 4. 2 to the power of 3. Well, that's going to be 2 multiplied by itself 3 times. 2 times by 2 is 4, times by 2 is 8. It's also worth mentioning b to the power of 0 is always 1. So if b was 10, 10 to the power of 0 is 1. 365,000 to the power of 0 is 1. b to the 0 always equals 1. Okay, now let's substitute in some values. In our case, b is the number base that we're in. So I am working in base 10, so b is 10. Now, the first column is easy, it's 1, because remember, b to the power of 0 is always going to be 1. So, in any number base, the first column is 1. Now we've got 10 to the power of 1, which is just itself 10. b to the power of 2, 10 to the power of 2, 10 times 10, which is 100. 10 to the power of 3, which is 10 times 10 times 10, which is 1000. You can see that this is 10 times bigger than this column. You just get 10 times bigger every single time. And you'll probably know that you just add a 0 on if you're timesing by 10. I think it's pretty easy to continue filling out the columns, so I won't bother talking you guys through it.
I'm doing base 2, so in this case, b is 2. Let's fill in the columns. 2 to the power of 0 is 1. 2 to the power of 1 is 2. b to the power of 2 is 2 times 2, which is 4. 2 to the power of 3 is 2 times 2, which is 4, times 2 again, which is 8. As you can see, we're just doubling each time. 2 to the power of 4 is 16. Or you can do 2 times 2 times 2 times 2, which is 16. 2 to the power of 5, which is 2 times 2 times 2 times 2 times 2, which is 32. We're used to working in base 10, but what about this? This is a binary number. Pause the video and see if you can figure out the value. I mean, what is this number in base 10? This may look, on its own, as we know, the number 11. If we put it in its columns, we can see we've got 1, 1, and 1, 2. 1 and 2 equals 3. So the binary number 1, 1 is actually equal to the value 3. So let's try. Pause the video and see if you can figure out what this binary number is in decimal or base 10. I've drawn a line down here to make it easier to read. Well, there's 1 in the 32 column, so there's 132. Well, we've got nothing in the 16s column, nothing in the 8s column, 1 in the 4s column, so we add 4. We've got 1 in the 2s column, so we add 2. And nothing in the 1s column, so no 1s. Let's add them up. And the answer is 38. So the decimal number 38 is equal to the binary number 100110. What if you wanted to convert the decimal number 43 into binary? Usually I'll find the first column that exceeds 43, or the number you're trying to convert. The next column is b to the power of 6, which is 64. And 64 is bigger than 43. So if we put a 1 in this column, our binary number is going to be too big. 64 is bigger than 43, so we can't put a 1 in there. We can put a 1 in 32, because that's smaller. Now we only have 11 to make up, because 43 minus the 32 we have is equal to 11. If we put a 1 in the 16s column, our number's going to be too big, so we'll put a 0 there. We still have 11 to make up, so we can put a 1 in the 8s column. Now we only have 3 to make up. We can already see that 4 is going to be too big, so let's put a 0 in there. We still have 3 left, so let's put 1 in the 2s column, and this works out perfectly. It's 1 left, 1 in the 1s column. So the decimal number 43 is equal to the binary number 101011. Let's try another number base. Let's go with hexadecimal. People also call it hex and base 16. Base 16, as you can probably guess, has 16 digits. 0 to 9, but that's only 10 digits. We still need 6 more. And remember, you can have any symbol, but we just use A to F. A is worth 10, B is worth 11, C is worth 12, and so on, till F, which is 15. Let's work out the decimal number 27 in hex. The first thing we need to do is draw out our column. Point goes here. The first column on this side of the point is b to the power of 0, then we'll do b to the power 1 and b to the power of 2. Anything to the power of 0 is 1, so let's do 1 here. So in base 16, 16 to the power of 1 is 16. Remember b is 16 because we're in base 16. b to the power of 2 is 16 times 16, which is 256. Even if we put a 1 in this column, it will be 256. It will be way too big. Let's go into the next column. How many 16s are in 27? Well, that's just 1, with a remainder of 11. So put a 1 in here, and now we just have 11 to make up. Now in the ones, we've got 11 ones to make up. So B is actually worth 11. So let's put a B in here. So we have 11 ones. So the decimal number 27 is equal to the hexadecimal number 1B. Let's do it the other way around. Let's convert the hex number 2D to a decimal number. I've drawn it in our grid for us. It's 2 in the 16s column, so we need to do 16 add 16. We've also got D in the ones column, and D here is 13. So we've got 13 ones, so add 13, which equals 45. Sorry about the quality of my fives. So the hex number 2D is equal to the decimal number 45. We've done binary to decimal, decimal to binary. We've done hex to decimal and decimal to hex. But what about binary to hex and hex to binary? You can already convert from any number base to any other number base. Let's say we want to convert this number 212 from base 3 to base 8. Remember our columns? We can use these to turn it into base 10. The base is 3. Fill out the columns. You know how to do that now. 2 9s are 18. Add 3, which is 21. Add 2, which is 23. So in 212, in decimal, is 23. Now we just need to turn this to base 8. Back to our trusty board. We're trying to make 23 in base 8. So 3 8s are 24. That's 1 too many. So 2 8s are 16. Let's put 2 in here. Oops, that's a bit weird. And we need 7 more then. So let's put 7 in the ones column. 212 in base 3 is 27 in base 8. You can convert to any number base you dream of without memorising.
You can already convert from binary to hex and back again, but we would like to give you some insights on binary and hex. As you already probably know, binary is the language of computers, and there's an interesting and helpful relationship between binary and hex. You're probably aware that each one of these binary single digits alone is called a bit, and 8 of them together is called a byte. You're also probably aware that there's a name for 4 bits. If you don't know what it's called, have a guess, bearing in mind that is half a byte. It's called a nibble.
Hilarious, don't you think?
Each nibble can be represented as 1 hex digit. If we think about this nibble as a binary number on its own, it's a 2 and a 4, which is 6. Let's do this nibble. It's a 1 and a 2, no 4s and an 8, which is 11 in decimal and B in hex. You can have a huge binary or hex number, and if you break it down into nibbles, you only have to add up to 15. Let's convert a really large number. This number here is a hex code I used to light my LED earlier. If you see a 0x in code, it means it's a hex number. And if you see a 0b in code, it means it's a binary number. This is true in many programming languages. For definite, Python, C++ and JavaScript. Let's start with the first nibble. That's E. And in binary, that's an 8, 4, 2 and no ones. Next nibble's the same. These next two nibbles are easy, it's just 4 zeros and 4 zeros. A 2 is no 8s, no 4s, 1, 2 and no 1s. And 1 is just 0, 0, 0 and 1, 1. So here we had 6 nibbles, or 1, 2, 3 bytes, or 24 bits. With just 3 bytes, you can have numbers over 16 million, which can get a bit taxing from converting hex to decimal to binary and then back again. But with a nibble trick, you only have to add up to 15. How many different combinations can you have with a certain base with a certain amount of digits? Well, you get your base and raise it to the power of the number of digits you have. We were just in base 2 and had 24 digits, which gave us this number up here. The biggest number we can represent is 1 less because we have to represent 0. This works for any base, any number of digits. We were also working in hex, which is base 16, and we had 6 digits, and 16 to the power of 6 is also this number up here. Hopefully that's given you a deeper understanding of a relationship between binary and hex.
We've only converted numbers on this side of the point. What if we go to this side of the point?
Notice, as we move up a column, our exponent, this little number here, increases by 1. So we go from b to the power of 0 to b to the power of 1, b to the power of 2, and it keeps on following that pattern all the way in this direction. And of course, as we go down, it decreases by 1, b to the power of 1, b to the power of 0. So what's this column going to be here? Well, you guessed it, b to the power of minus 1. What's the next one going to be? Well, move down 1 again, so b to the power of minus 2, b to the power of minus 3, b to the power of minus 4, and so on and so forth. And that it keeps following that pattern all the way in this direction. Most of you will probably know about negative numbers and negative exponents and how to work them out, but if you don't know what negative numbers are, then that's fine. You can still follow along with this video and you can still do this. And also, if you don't know what negative exponents are, then my sister's got an in-depth video about indices in general and negative exponents and how to work them out, but I'll just go through them very briefly just now, and I think you guys will find that it's not too complex. So let's take b to the power of minus 1 for example. That is just equal to 1 over b to the power of 1, which is just itself b, so just 1 over b. b to the power of minus 3, well that's just equal to 1 over b to the power of 3, which is equal to 1 over b multiplied by b multiplied by b. 2 to the power of minus 2, that is just equal to 1 over 2 to the power of 2, which is equal to 1 over 2 multiplied by 2, which is 4. Well, since we're in decimal, which is base 10, b is 10. So this is going to be 10 to the power of minus 1, which is equal to 1 over 10 to the power of 1, which is just equal to 1 over itself, 10. So we'll put that in our column, 1/10. Next column is b to the power of minus 2. b is 10, so it's going to be 10 to the power of minus 2, which is 1 over, you guessed it, 10 to the power of 2. 1 over 10 times 10, which is equal to 1 over 100, or 100th. Again, most of you will have already spotted this, but there's a pattern here. As we move up a column, we get 10 times bigger, or just times by 10. When we move down a column, you guessed it, we get 10 times smaller. So 10 times smaller than 100 is 10, 10 times smaller than that is 1. So if you move down a column, you get 10 times smaller, or just divide by 10. Again, if we move down a column from 1, we're going to get 10 times smaller, or divide by 10 is just 1 over 10 or a 10th. 10 times smaller than that, and 100th. So I'm pretty sure most of you can guess what's going to come next. Yeah, it's 1,000th and 1,000th. So we're back in binary, and the point is here. It's a little bit large, sorry. As we know, our exponent, as we go down a column, is going to decrease by 1, e to the power of 0, minus 1, minus 2, minus 3. Of course, remember, this carries on going forever in that direction and forever in this direction. So of course we're in base 2 now, so b is going to be 2. So this column is going to be 2 to the power of minus 1, which is equal to 1 over 2 to the power of 1, which is just 1 over 2, or a half. So let's check if we're right. In base 10, moving off a column, we got 10 times bigger. So in base 2, we should get 2 times bigger whenever we move up a column. 2 times bigger than 2 is 4. 2 times bigger than 4 is 8. It does work in any base. In base 2, as we move down a column, we should get 2 times smaller, or just divide by 2. 8 divided by 2 is 4, and 1 divided by 2 is a half. So what's our next column going to be? Well, we can predict it's going to be a quarter, 1 over 4. Ooh, where's the pen? Let's check we're correct. b, which is 2 to the power of minus 2, is equal to 1 over 2 to the power of 2, which is equal to 1 over 2 times 2, which is 4. So we're correct, it is 1 over 4, or a quarter. So the next column down is going to be 2 times smaller than a quarter. So that's going to be an eighth. 8. I'm back in decimal, or base 10, and when I was younger, my class and I got told that we had to memorise 0.5 equals a half. At the time that was a bit confusing, because what does a 5 have to do with a half? But when I learnt this, I could then see that 0.5 was equal to 5/10, and then I could see how 5/10 was equal to a half. These are supposed to be tenths, by the way. I'm back in binary, or base 2, and let's see if we can figure out what 0.5, or a half, is equal to in binary. Well, it's going to be smaller than 1, so we've of course got to do our 0 and then a point. And the first column to the right-hand side of the point is a half, so we'll just put 1 in there. So the binary number 0.1 is equal to a half. Well done, you made it. You sure know a lot about number bases. You should now be able to work out base 64, but that just has a load of symbols, uppercase, lowercase, other symbols. There is such thing as base 64 encoding, which is what we showed you in the email, and there's a video in progress on that now. If you're not watching this new, then hopefully there should be a video already out, but if you're watching this new, then there'll be one coming very soon. There will be that small percentage of geniuses who get this straight away, and then there'll be most people who might have to rewatch this video, and then there's the people like us. We've had this lesson numerous times and we still didn't get it. Our dad had to explain it to us so many times before we actually clicked on. So if you are like us, then you might have to rewatch this numerous times, but stick with it because it is worth it. It's also really important to practice.
So we might leave some questions in the comment box down below.
And it's absolutely normal to make mistakes, so don't be put off by that either. We made so many mistakes before we got it right.
Remember our code from the beginning of the video? Well, here it is. Here is a list of hex numbers. All you have to do is convert them into binary numbers. If a digit is 0, it's blank, and 1, you fill the square in like that we're showing down here. So for example, if this number here in binary was 000000001, all of these squares would be blank and this one would be filled in. Comment what the emoji is in the comment section down below. Please give this a go because it'll be very helpful with your understanding on this topic. You should be able to do this, but if you're finding it a little bit tricky, we've got a tool on our website which should help you out a bit.
If you like this video, please give it a big thumbs up and subscribe to our YouTube channel. Have a good day. Bye!
Bye!